Hello all, and welcome to our first LEGO League virtual camp. This video accompanies the Day 1 activities and will cover some introductory topics. Today, we'll be learning about the general engineering design process. This will provide a framework for how to think about building your FLL robot. We'll explore a few tips and tricks specific to FLL and LEGO robots. And finally, we'll spend some time looking at the operation of gears, one of the most common parts of a LEGO bot. We'll start with engineering design and process. We start by spending some time thinking about how to think. Engineering design is the process by which we arrive at a solution for a given problem. Though not the only way to create a solution, it's usually a very effective method. It helps ensure the final product is the best it can be. Because design is a process, it involves going through a sequence of steps, one by one. Engineering design process can be applied to anything, but it works particularly well for FLL, where you have a well-defined problem and need to produce a solution. Most design procedures will follow these basic steps. First, you start by understanding your requirements. You learn the rules, what sorts of things you can or can't do, and what sorts of things you need to accomplish. A careful understanding of requirements ensures that you can focus only on valid solutions. This will help focus your solutions to solve the problem the best that you can. Once you understand the requirements, start making plans for what you will do and what you won't. Decide for you which steps are the most important and which will be least important. This will ensure that you spend your time by solving the most important parts of the problem and ensuring you don't get distracted by things that don't really matter. Once you know which portions of the problem are important, you begin by doing research. Start to see what other people have created. See if other people have created similar or related solutions already. Write down where you find good and useful information, and talk to your teammates about what you find. Now, it's time to start building. Gather your materials and start experimenting. Build something you've seen before, or let your imagination run wild. No idea is too crazy to try at this point. Go fast, iterate quickly, and keep good records of what worked well. After many rounds of building and testing, share what you believe to be the best option. Make it strong and robust, ensuring it can survive the rigors of competition. Make sure it works many times, the same way each time. Once you're confident it will work, it's ready to be brought to a competition. In the engineering world, we call this moment going to production. It's the moment we take our solution and put it out in public. There's no going back and no more iteration. However it works out in the real world is how it's going to work. Hopefully, if we've done our job well, we'll have lots of success. And we certainly do hope for that, especially at our competitions. But regardless of how well we do, or how badly our plans fall apart, it's always important to review afterwards as a team. What went well, and what could we do better next time? Write this down and use the lessons learned for your next competition. We'll now go into some ideas for your FLL robot designs. It's good to add your own requirements to the ones you are given. By carefully setting your own goals during the design process, you can define not just what you will accomplish, but how you will accomplish it. Knowing exactly what to do takes many, many years of experience, and a good chunk of luck, too. But, even if you're new, there's some general principles you can still follow. Designing for maintenance. It's a fact of life that things are going to break. No matter how well you design your robot, you'll have pieces fall off, shafts twist and bend, and wheels wear out. For the first line of defense, choose designs that don't break as often. Sturdier is usually better. Then, for things that are likely to twist or break or wear out, ensure that it's easy to replace those parts. For example, if you need to change your wheels a lot, don't put a big case around them that you have to disassemble just to get to the wheels. Design for repeatability. Robust designs are ones that keep working many times in a row. Their operation is repeatable. You want to ensure that your robot works the same way every time you run it. Minimizing variance in how it operates allows you to perform consistently on the table and makes planning strategies easier. There's a lot of techniques that go into making your robot robust, but there's a handful of things that do show up quite commonly in FLL. A jig is a set of Lego pieces which ensure the robot is always started in the same position. You can build them and bring them to the field with you to ensure you always place your robot properly before starting a mission. Be sure to read the rules for any restrictions on how big your jig can be and how you can use them. Additionally, when designing mechanisms, look for designs that work from many angles, as well as if they're slightly offset to the right or left. You don't want to choose designs that require lots of precision to align. Self-centering is the term people often use to describe mechanisms which naturally move towards your goal rather than away from it. Another good, simple technique for ensuring your robot is pointed in the right direction is to use the walls. By briefly driving into the wall or driving along the side of it, you help ensure the robot remains pointed straight. Sometimes we call this mechanical alignment. Designing for swap speed. A very common technique in FLL is to use multiple attachments for different missions. If you do choose to follow this design, one thing to keep in mind: how long does it take to take off one mechanism and attach another? If you have to adjust 8 different attachment points during every swap, you'll lose valuable time that could have been used to complete a mission. The faster you get your parts on and off, the better. Dog gears are a good way to transfer power to a mechanism without having to carefully attach shaft or wires. Balancing speed and precision. Doing things quickly is important, but not at the expense of not completing the mission. Push your robot to be fast, but not so fast that you have to attempt the mission 3 times before succeeding. You want to experiment with different motors, gears, and software to keep the robot quick but accurate. We'll talk more about gears later. Always check the rules to ensure your motor selection is legal for this year. And finally, do your research. This is one of the steps that we talked about in the engineering design process, but it bears repeating. Read books, research websites, and look for YouTube videos about the problems you're trying to solve. Explore around for ideas. Don't feel like you have to invent everything on your own. You can research what others have done and use it as a starting point for your own designs. Take their suggestions and use them to make the robot even better. We'll now move on to discussing gears. These are some of the basic building blocks for robots. So first off, what is a gear? Gears are circular components attached to a shaft and have teeth. Usually you use 2 or more and position them so their teeth are meshed together. As one gear turns, it pushes on the teeth of the other. This in turn makes another shaft spin. It's effectively a spinning lever. Spur gears are the most common type and what most people think of gears as. Spur gears change the direction of motion. They also can change speeds and move where the motion is at. Bevel gears are much like spur gears, but their teeth are a slightly different shape. This allows you to mount them so that they transfer motion at a right angle. Worm gears have a high reduction in a very small space. Worm gears can generally only be driven from the smaller gear side. That's where the motor is pointing in. These are very good at locking mechanisms, where you need parts to stay in place after you turn off the motor. As you probably noticed from the previous slides, the shafts attached to gears were not all spinning at the same speed. This is generally true. If gears are not the same size, their shafts will spin at different speeds. We'll go over the actual math in the next slide, but the concepts are more important. Just remember, the smaller gear always goes faster. It's pretty simple. If you have 2 gears in mesh and you spin them, the smaller gear will always be spinning faster. Assume that we had a tiny gear and a big gear in mesh with each other. If you twist the big gear by hand, you'll see the tiny gear start spinning really fast. But if you spin the small gear by hand, you'll see the big gear go really slow. For all of the cases that I know of in FLL, you want the smaller gear attached to the motor and the bigger gear attached to your mechanism. If you'd like to see the math, here's a bit of it. The gear ratio is actually a number, which you calculate. To calculate it, simply divide the number of teeth in the motor gear by the number of teeth in the mechanism gear. Usually you convert this number to a decimal. Gear ratios between 0 and 1 mean that the gears will reduce the speed of the motor. Gear ratios above 1 mean that the gears will increase the speed of the motor. This number is meaningful. It tells you, for every rotation of the input shaft on the motor side, how many rotations happen at the output shaft on the mechanism side. Let's do a quick example. As you can see, the motor is driving an 8-tooth gear, which is in mesh with a 40-tooth gear. The 40-tooth gear turns the mechanism. To calculate the gear ratio, we take 8 and then divide by 40. This yields a gear ratio of 0.2. We then use this number to understand how much the speed changes through the gears. Every rotation of the input shaft will yield 0.2 rotations at the output shaft, or, equivalently, 5 input shaft rotations are needed to get 1 output shaft rotation. Alright, we have a tiny bit of homework for you to do before the first class. It's optional, so no worries if you don't have time for it or you don't have your kit. But for those of you who do have the parts and the time, first, grab a few parts from your kit, including at least some gears, some shafts, and some parts to hold it all together. Assemble the parts so one gear is enmeshed with the other. Check the number of teeth on each gear. Compare to pictures or count by hand. Try to calculate the gear ratio. Then, grab the shaft attached to the smaller gear. Do you expect the big gear to be going faster or slower? Turn the shaft of the small gear and check your answer. Bring any creation you have to class and we'll talk about them. In conclusion, today we've done a good bit of learning about design process. We've seen some examples of pointers for good FLL design and have done a deep dive on gears and gear ratios. Be sure to bring any questions you have to our live session. We'll review this video, your homework, and try to answer any questions you have. Thanks!